When you tap a button to order food on a busy Friday night, you expect the application to respond immediately. Modern digital experiences are built on the expectation of instant execution. Behind that button press is typically a synchronous microservice architecture. When the central order API receives your request, it triggers direct, sequential calls to every other service, reaching out to payment, then inventory, and finally notification. This creates a strict dependency chain. The central order service cannot move forward and tell the inventory service to reserve your food until it receives a successful response back from the payment service. If the notification service experiences high traffic and slows down, or goes completely offline, the entire chain breaks. The order service gets stuck waiting for an answer. Because the order service is blocked waiting for that notification response, the execution thread stalls. On your end, the app freezes, and you are left staring at a spinning loading wheel. To compensate for these blocked threads during a traffic spike, companies must provision massive servers whose only job is holding idle connections open. End users should never be forced to wait for background system tasks to complete. Synchronous architectures tie the user's experience to back-end delays, making them a liability for high-scale background processing. To resolve this microservice gridlock, engineers turn to Apache Kafka, an open-source, distributed event streaming platform. While it is often confused with a traditional message queue, Kafka serves a distinct architectural purpose. Kafka functions as a durable, distributed log. It acts as a highly resilient, centralized buffer that sits between your services. By placing this buffer in the middle, the act of generating data is separated from the act of processing it. The order service simply logs that an order occurred, and its job is done. Placing a high-throughput event buffer at the center of a system removes synchronous wait times. This decoupled approach is the required foundation for modern event-driven architecture. Any system emitting data is a producer. It sends data and moves on without waiting. The server receiving this data is the broker. Inside, data organizes into logical channels called topics, like one dedicated to food orders. But if a single topic attempts to process millions of incoming events sequentially, one by one, it immediately becomes a new bottleneck. To solve this, Kafka splits the single topic into multiple parallel lanes called partitions. Incoming data packets are distributed across these lanes, allowing Kafka to process massive throughput simultaneously and bypass the limits of sequential execution. Partitioning is the specific choice that turns Kafka from a basic data pipe into a massively scalable parallel execution system. Inside each partition, data is written to an immutable, append-only log. Once a data block drops in, it locks solidly into place. It cannot be overwritten. Each block receives an increasing integer label called an offset, acting as absolute coordinates. This design contrasts with legacy message brokers, which rely on a push-based first-in, first-out mechanism. In traditional queues, once a message is pushed to a system and processed, it is typically deleted from the queue immediately. Kafka relies on a pull-based consumer model. Data is durably written to the server's disk, and consumers must proactively request to read it. This durable pull prevents downstream services from crashing under forced data loads. They pull information only when they have the capacity. With data durably on disk, Kafka enables fan-out. Multiple services read the exact same event at their own pace. Payment races to offset 5, while notification slowly processes offset 3. If inventory crashes, it simply reconnects and resumes from its last recorded offset. Because the data stays durably on disk, services can even rewind their offset to replay historical data, which simplifies recovery from database corruption. The pull-based fan-out model breaks the synchronous bottleneck, granting absolute operational independence to every microservice in the ecosystem. There is still one final vulnerability. If a single Kafka broker suffers a hardware failure, the entire event stream halts. Brokers are grouped into a Kafka cluster, a distributed network working in unison. Through partition replication, exact copies of data are maintained across different physical hardware. If broker 1 goes dark, traffic instantly reroutes to broker 2 with zero data loss. Historically, managing these clusters was complex, requiring a completely separate system called ZooKeeper to manage the cluster metadata. The Kafka 4.0 release marked a major milestone by implementing native cluster management and controller elections via KRaft mode. Running strictly in KRaft mode eliminates the operational overhead of ZooKeeper entirely. Partition replication, combined with KRaft's native management, makes Kafka a self-sufficient, highly reliable distributed engine capable of surviving hardware failures. To see this architecture tested at scale, consider a modern highway management system tracking millions of vehicles simultaneously across multiple lanes. Overhead sensors must capture speed, weight, and classification events in real time. Provisioning enough synchronous servers to process millions of these IoT events per second instantaneously would require a massive overinvestment in compute resources that remain idle most of the day. Instead, the Kafka cluster acts as the system's shock absorber. It ingests the high-velocity telemetry stream via its parallel partitions. Asynchronous worker nodes pull and process this durable data at their own pace, methodically working through the backlog even during low traffic hours. Using Kafka as an ingestion buffer decouples cost from peak demand. Instead of provisioning for the maximum traffic spike, a business can maintain a smaller, steady fleet of servers that process the backlog as resources allow. Kafka functions as a persistent distributed log, maintaining a his system state that remains available long after an event occurs. Its design, an immutable partitioned log paired with a pull-based consumer model, shifts the burden of processing away from the source. This architecture forms the backbone for platforms like Netflix, Uber, and massive IoT sensor grids. Kafka transforms fragile, tightly coupled microservices into resilient, scalable, event-driven ecosystems capable of processing trillions of operations every single day.